Hi everyone, today we're going to be talking about the chemistry of igneous rocks. So let's start with modal or modal versus normative or norm mineralogy. Here we can see that mode is the relative abundance of minerals in a rock by volume percent. And so we can see that down here on this graph here. And the IUGS classification system that we talked about in the first igneous petrology video, the one over igneous rock classification, is based on volume percent or mode as well. And all of the classification diagrams and everything we talked about in that video are based on mode or modal mineralogy. But because obtaining volume percentage values for fine-grained rocks or more volcanic rocks rather than plutonic rocks is difficult, we use norm or normative mineralogy for these rocks. And that just means that we take the abundances by weight percent rather than volume percent. And instead of the mineral relative abundances, we actually look at the relative abundances of major element oxides. For example, we look at iron oxide and magnesium oxide versus calcium, sodium, and potassium oxides for more mafic versus more felsic compositions, etc. And then we kind of get more specific as we go. And we're going to talk about all of the element oxides we look at today, as well as how we look at them in terms of their relative abundance by weight percent and what this can tell us about the history of formation of that rock and its source magma and all of that. So let's get started by looking at the major elements in igneous rocks and how those can tell us about the history of the magma differentiation of the source magma that rock formed from. So let's talk a little bit about what this means, magma differentiation, because this is where igneous rocks begin to differ in their composition, even though they're from the same parent magma. So we talked about differentiation and fractional crystallization in the silicate magmas video, where we talked about how you have a magma chamber, and as the magma chamber cools, it goes down in temperature, and at each down step in temperature, a different mineral decides to crystallize because minerals crystallize at different temperatures. This is the basis of how magma differentiation works, and we can see here that olivine is one of the first minerals to crystallize out of the cooling magma because it doesn't like to be melted at any temperatures below 1200 degrees Celsius, clearly. And then as you get cooler, you get some other minerals that decide to crystallize out of solution because now it's their temperature, it's their time to shine. And then you get cooler and cooler and more of the other minerals start to come out. And we can see here that we're getting more mafic to more felsic minerals as we make the temperature lower. So the first ones to cool and crystallize are more mafic, like olivine and pyroxene, and then you get plagioclase feldspar and eventually more felsic feldspars as you go down in temperature. And this is called fractional crystallization, when you have things crystallize out and they kind of are taken away from the system or are separated in these kind of layers we can see here in the magma chamber forming from the rest of the remaining residual magma solution, if you will. Oh, whoops. I clearly had some more arrows here that I missed, but we also talked about how this works, how different minerals cool and melt at different temperatures and why that is in the phase diagrams video. And then obviously this is a depiction of fractional crystallization, which we just talked about. And moving to compatible and incompatible elements. This gets into now what we're going to be talking about in this video, which is the chemistry of igneous rocks controlled by major elements that are incorporated into the crystallizing crystals. And what elements these are depends on whether they're compatible or incompatible, which depends on things that we'll get to later in the video. But the general gist of what a compatible element is that it's preferentially incorporated into the crystals that are forming from the cooling melt. So whatever elements that are preferentially incorporated into this olivine here that are crystallizing out of the melt, those are compatible elements. And those elements that are preferentially, staying in the melt because they can't fit in the crystal lattice or whatever of the olivine or whatever crystals are coming out of the melt, those are incompatible elements. And those elements are basically just incompatible with fitting into those crystals that are crystallizing from the magma. So we'll talk more about compatible and incompatible elements and why they behave this way, either compatibly or incompatibly, in the last section in this video when we talk about trace elements and how they can get substituted into crystal lattices of minerals that are forming from these melts. So we'll get to that. But now let's get into some of the compositional variations we see in igneous rocks and how those help us to identify and classify igneous rocks. So the first minerals to crystallize from mafic melts are silica poor, and therefore differentiation causes the residual melt, the leftover stuff, to increase in silica content. And this means that basically silica is kind of behaving as an incompatible element. So we don't just have to think about the compatibility and incompatibility of these things as just elements. It also can apply to things like silica, which is a molecule, or basically the silica tetrahedra we've talked about in like all of the other igneous petrology videos if you're not clear on what that is, or actually the mineralogy videos will be good to check out if you don't know what silica is. But because we know silica's behavior, meaning it remains in the melt for as long as it can, we can then measure the concentration of other elements against silica percent to show their concentration change through increased differentiation, or basically kind of through time and differentiation of that magma chamber. What do we mean by this? Well, if we look at something called Harker diagrams, we can see that, for example, these element oxides, like we said we were going to look at the relative abundances of, we can see there's titanium, iron, magnesium, calcium oxides in these diagrams, and they're all plotted against the x-axis, which is silica weight percent. And this is 50 to 80% down here. And we can see that with increasing silica content, these elemental oxides specifically are going down, are decreasing with increased silica content. And this is basically showing that with increased differentiation in the magma chamber, the melt is becoming increasingly concentrated with silica, because we just said residual melt will increase in silica content, and it's becoming depleted in titanium, iron, magnesium, and calcium. And this is actually to be expected because typically ferromagnesium minerals and calcic plagioclase minerals, which contain calcium, iron and magnesium, and titanium, all decrease with increasing silica, or basically decrease with increasing differentiation in that residual melt, because they're becoming crystallized first and incorporated into those first crystallizing minerals. Additionally, aluminum-rich minerals shown here by aluminum oxides may also decrease, but the decrease of aluminum oxides isn't as intense or drastic as the ones we showed on the previous slides. However, alkalis like potassium and sodium, as shown here by potassium and sodium oxides, increase with increasing silica content. And this means that alkalis are also left in the residual melt for longer than the more mafic materials like ferromagnesium and calcium minerals, just as we'd expect, since these are more on the felsic side of things and therefore have more silica content, and therefore it makes sense that they follow the trend that silica follows. So these Harker diagrams are not the only way that we can reconstruct the differentiation history of magma. There's also major element indices, so major elements like the ones we just talked about, alkalis, calcium, magnesium, iron, and aluminum. All of those elements are major elements in igneous rocks, and there are indices of differentiation that we can use to also help us understand the differentiation history of magmas based on compositions of rocks. And here we can see the 5 ones we'll talk about today are the alkali-lime index, the iron-enrichment index, the aluminum saturation index, the alkalinity index, and together with the alkali index, we'll talk about the feldspathoid-silica saturation index. So the alkali-lime index is based on relative abundance of calcium oxides, sodium oxides, and potassium oxides, which are all important constituents of feldspar. And in this index, we have these rules here that state that if calcium oxides are more abundant in your magma chamber, the first feldspar to crystallize from the melt will be anorthite, or basically calcium feldspar. And if alkalis are more abundant, the feldspars that form first will be albite and orthoclase, or sodium feldspar and K-spar, or potassium feldspar. And the resulting rocks can be classified into 4 different terms. These terms include alkalic, alkalic-calcic, calc-alkalic, and calcic. And we can see these 4 terms are based on silica percentage. Now, this may become confusing because you're like, okay, well, we just talked about how it's just based on calcium and alkalis and their relative abundances, but we can classify them based on on silica percent, because where the calcium oxide and sodium plus potassium oxide curves, as shown on these Harker diagrams, intersect is at a specific point on the x-axis, which will give us a silica percentage value. So this silica percentage value on the x-axis, where the calcium and sodium and potassium or alkali curves intersect, which can be done if we just plot those dots on top of each other, where those intersect is thought to be the silica content percentage that will then help you identify which of these four categories your end product rock fits into in the alkali-lime index. And if it's less than 51% silica, so if those curves intersect on the x-axis where it's less than 51% of silica, so on these it would be like way over here on the lower side of the silica content on the graph, that would be an alkalic rock, and that would basically mean it's more abundant in alkalis than it is in calcium. And then you can see alkalic calcic is within the 51 to 60% range of silica if they intersect in there. And then in the calc-alkalic category, they have to intersect within the 56 to 61% range. And in the calcic category, they have to intersect past 61%, a very high silica content value. And that would mean it's very calcic and very depleted or relatively depleted in alkalis like potassium and sodium. We can also identify or understand the history or content of a rock based on its iron enrichment. And this is the iron enrichment index. The iron enrichment index can show whether a rock has undergone, or basically a magma chamber has undergone, a ferroin trend or a magnesian trend. This just means that in the case of the ferroin trend, the rocks undergo iron enrichment before alkali enrichment in terms of what's crystallizing from the melt. And in the magnesian trend, the rocks basically just undergo minimal iron enrichment. And so we can see that we can plot the iron enrichment index, which is this formula here shown by the iron or Fe star, and then plot that against silica weight percentage like we always have. And we get this line of the iron enrichment index showing that if your data plots above it, it's a ferroin trend. And if it plots below it, as does the current data in this graph, it would be a magnesian trend. So from this, we can tell that these data are showing a magnesian trend, meaning the rocks underwent minimal iron enrichment throughout the differentiation of the magma chamber. And this can tell us something about the redox conditions in that melt, in the parent melt or the source melt or magma that formed those rocks. And what that means, if you're not sure what redox means, it's basically reducing versus oxidizing. Oxidized melts are melts that have more oxidized material, like for example, iron can be an oxidation state of +3 or +2. +2 is reduced iron, +3 is oxidized iron. And so magma chambers or melts with more of the oxidized versions of these elements are classified as oxidized melts, and those with more of the reduced versions are classified as reduced melts. And so reduced melts typically follow a ferroin crystallization trend, meaning that data would plot above that line there, whereas oxidized melts typically plot below the line in a magnesian trend, and that's why these data probably represent an oxidized melt. Moving to the aluminum saturation index, the ASI indicates whether there's an abundance of alkalis over aluminum or vice versa, whether there's an abundance of aluminum over alkalis or sodium and potassium. If you remember our alkali-lime index, those alkalis are sodium and potassium mainly. So in most mafic rocks, neither alkalis or aluminum are present in excess. And so what they're classified as is metaluminous, whereas granitic rocks can be either metaluminous, paraluminous, or even paraalkaline. And we'll talk more about paraalkaline in the alkalinity index in the next slide. But in terms of metaluminous versus paraluminous, it's basically when there's neither or excess in the case for the metaluminous category, or there's excess aluminum over alkali. And if we plot the ASI formula or aluminum saturation index against silica weight percentage, percentage like we have been for the x-axis the whole time, we can see where the lines are for paraluminous versus metaluminous and where the data plots, and you can kind of get a sense over the time of differentiation, which we can tell is increasing with increased silica content in the residual melt. We can get a sense for where it crossed over to paraluminous material versus where it started at metaluminous material, or if it ever even got to paraluminous material, giving us a sense for how aluminum and alkali-rich the parent melt or magma source was. But what about these para-alkaline values? What determines whether something's para-alkaline? Well, it's excess alkalis over aluminum, and this brings us to the alkalinity index, in which we also have to talk a little bit about the feldspathoid-silica saturation index, or FSSI. In terms of the alkalinity index, or AI, it's this formula, basically aluminum minus the alkalis, and that gives us a sense for how much aluminum over alkali content there is, or vice versa. If there's more aluminum than there are alkalis, this will be a positive value, plotting positively on this little plot here, and they're called metaluminous, like we talked about. Whereas if it's para-alkaline or there's more alkalis than there are aluminum, it will be a negative value and plot on the bottom or negative side of this plot here, and these are labeled para-alkaline. But this plot also takes into consideration the FSSI and whether the value should be negative or positive for that. And that basically, as you can see by the other stuff on this plot, is based on silica saturation. So basically quartz excess over lucite and nepheline minerals. And we can see that it's positive for quartz saturated rocks and negative for silica undersaturated rocks. And the minerals contained within each of these rock types would be for metaluminous silica undersaturated rocks, nepheline and calcic pyroxenes and amphiboles. And then for metaluminous silica saturated rocks, it would be quartz, ferric pyroxenes and amphiboles, magnesium pyroxenes and amphiboles, as well as calcic pyroxenes and amphiboles. And then for para-alkaline silica undersaturated rocks, it would be nepheline and sodic pyroxenes and amphiboles. And then for para-alkaline silica saturated rocks, it would be quartz and sodic pyroxenes and amphiboles. And just by the way, ferric means containing iron, magnesium means containing magnesium, calcic means containing calcium, and sodic means containing sodium. And none of these terms really exclude the other possibilities. Like if you say there's ferric pyroxenes, it doesn't mean there aren't magnesium pyroxenes, but it just means they're most abundant in iron and vice versa. So those are those terms. And now let's move to the last part of this lecture, which is about trace elements. Trace elements can be extremely useful for identifying the conditions and processes that led to the formation of igneous rocks. And this is because trace elements, which are only less than or equal to around 0.1% of the final rock, show a drastic concentration change depending on the rock's conditions and processes of formation compared to that of major elements. For example, if a major element is a major constituent of the minerals within the rock, then its concentrational changes aren't going to be as drastic or as detectable as those shown by trace elements, which are only present in such small amounts and can drastically change in their concentrations. So common trace elements in rocks include many of the transition metals as shown down here in the periodic table, and rare earth elements as shown in the lanthanide series, and other trace metals on the periodic table of various types. And there's even more that I'm missing, but these are the general common trace elements. And the trace elements are partitioned between the minerals and the melt, giving us an idea of how to calculate how much trace element is incorporated into the crystal versus the melt. So this just means we can calculate the partition coefficient, or D, which is the concentration of the trace element I, Ci in the mineral, over that of the trace element in the melt. And we talk about this partition coefficient value in the strontium isotopes video, and we talked about in that video that the radius, size, and charge of the trace element controls whether that element can substitute for major elements in the mineral lattices. For example, if we look down here at the calcium 2+ ion, we can see that this is obviously a major element in igneous rocks, and if it's present in the magma and present in the forming crystal lattices, maybe some of those sites where the calcium ions want to fit into the forming crystal lattice can be substituted with different ions of similar size and similar charge. The strontium ion, for example, is 2+ charge, therefore the same as calcium ions, and has has a similar size, 132 versus 114 picometers, and therefore could be a good substitution ion for the calcium if the opportunity presents itself. Whereas rubidium, as shown here, would not be a great option because it's much larger in size and it only has a +1 charge rather than a +2 charge and wouldn't chemically like to fit in that spot. This brings us back to what I mentioned at the beginning of the lecture, compatible versus incompatible elements. This means that compatible elements that concentrate in the mineral have a high partition coefficient, or D value, as mentioned up here, because more of the trace element will be incorporated into that mineral rather than melt and form a high D value. So their partition coefficient is high, whereas the incompatible elements will have a low partition coefficient because they just want to stay in the melt. So that is it for today's video over the chemistry of igneous rocks and just basically the indices of differentiation that we talked about. But if you want to know more about how we classify igneous rocks based on their chemistry and modal mineralogy, I talk a lot more about that in the igneous classifications video, which I mentioned at the beginning of the lecture. So please go check that out if you want to know more. But in my upcoming igneous petrology videos, we will talk about stable versus radiogenic isotopes in the next one, and then basalts and the mantle in the following video, which I don't even have a thumbnail for yet, but that's going to be following that. And the two major references I'm using to make this video are Earth Materials by Cornelius Klein and Anthony Philpotts, which I'll link down below in the description, as well as the Essentials of Igneous Petrology by Ronald and Carol Frost, which I'll also link down in the description, as well as other minor references down there if you want to go check those out. And if you are still watching this video, please comment down below any extra topics you'd like me to cover for the Igneous Petrology playlist or any other playlist on my channel. And thanks so much for watching, and I will see you guys next time. Bye. If we look at calcium here. Okay.